Welcome back, class. Today we are going to visit a topic that we've talked about in both of the last couple chapters, and that is stoichiometry. And today we are going to look at how we can do stoichiometry with a chemical reaction where the reactants are gases and the information that we have involves the property of those gases. So, by using the ideal gas law, we can start with knowing the pressure, the volume, and the temperature of gas and convert it to moles, right? So what this presents, right, is a new method to establish moles, right? And that's really all about stoichiometry is because we have to get into moles so that we can do the sort of key part of stoichiometry, which is the center portion, right, where we convert from moles of one thing into moles of something else using that mole-to-mole ratio, the coefficients in our balanced equation. So far we learned how to go from grams to moles using the molar mass. And last chapter we learned how to go from volume of a solution to moles using the molarity. And now we're learning how to go from the pressure, volume, and temperature of a gas, things that we would commonly measure about a gas, into moles using the ideal gas law. Right? Now, on the second half of this, so sometimes we will mirror, right? We will want to know something about another gas. So we might want to know the volume of another gas that we make. Now, we also may want to know, grams, right? So we can mix and match these different methods, and we might have gas information about the initial one and use the ideal gas law, but at the end, maybe we want to know grams, and so once we get to moles of B, we're going to go to grams using molar mass. So we don't have to end up here, but we can if we need to. So let's look at a couple example problems. So the first one is, how many grams of water form when 1.24 liters of gas, H2, at STP completely react with O2? So we have information about hydrogen, right? We are told that 1.24 liters of hydrogen gas at STP completely react with oxygen. And we want to know grams of water is ultimately. So if we follow our sort of flow chart of what we need to do, so we have the information to start with, say, the pressure, the volume, and the temperature of hydrogen, go into moles of hydrogen. We can then use our stoichiometry to go to moles of water. And now that's for grams of water, so we could, of course, use the molar mass of water to go into grams of water. So we can sort of combine our stoichiometry techniques that we've been doing. Okay, so let's see how to approach this. Now, I want to point out something here. This is a special occasion, or a special situation, right? Notice we are at STP. Right? When we are at STP, something that we should always remember, right, is if we are at STP, we know that the volume, of 1 mole, right, equals 22.4 liters. So, and this only, of course, is appropriate at STP, but we can use this relationship here as a little bit of a shortcut so we don't actually have to go through the ideal gas law. And that would look something like this. Mm-hmm. So we'd start with our 1.24 liters of H2. Now, instead of using the ideal gas law to solve for moles, right, we know that 1 mole at STP is going to be equivalent to 22.4 liters. So now we have a way that I can get to moles just using the 22.4 liters. Now, the key to remember is this is only useful if we're at STP conditions, standard temperature and pressure. So now that we have moles of hydrogens, now we can continue on with the rest of our stoichiometry. And so now we need to move to moles of water from moles of hydrogen. So we're going to use our mole to mole ratio. So it takes 2 moles of hydrogen to make 2 moles of water. So we got a 2 here, a 2 here. And then the last part of our stoichiometry, we want to go to mass of water. So we got moles of water, grams of water, and we've done this before, but 18.02 grams per 1 mole of water. And if we do our math, we end up with 0.93, whoops, sorry, read that number wrong. We end up with 0.998 grams of water. And 3 significant figures, because that's what we had here. All right, so there's one example. So let's do one more problem, this one not at STP. So in this case, based on the reaction below, what mass of water, whoops, left out a word here, sorry, is needed to form 1.4 liters of O2 at 315 Kelvin, 0.957 ATM. So again, we're after the mass of water, and what we know about is the O2. So the first thing that we need to do is to get moles of O2. So our approach here is going to be to use the ideal gas law. Right? So we're going to follow our flow chart, if you will, and start with the pressure, volume, and temperature of O2. We're going to use the ideal gas law to get to moles of O2. Then we can do stoichiometry to get to moles of water, and then ultimately grams of water using the molar mass. Okay. So moles of O2 equals, so remember, ideal gas law, PV equals nRT, right? So N is going to equal PV over RT. So we have our P here of 0.957 ATM, right? That's the right units. And we have our V, 1.4 liters. We have our R, 0.08206 liter ATM mole Kelvin. And we have our T of 315 Kelvin. And of course our units cancel here, ATM on top, ATM here, liter, liter, and I have K and 1 over K cancel. So as we talked about before, we're going to end up with moles as our final unit here. we're going to calculate 0.0518 moles. We'll say I'm going to keep extra significant figures here because I don't want to make rounding error, and I'm just going to carry this number on in my calculations. So remember, it's okay to keep extra significant figures if we're going to continue to do multiple calculations, and then just make sure that we understand how many significant figures at the end. That in this case we're limited by the volume here only having 2 significant figures. So let's finish the stoichiometry. Oops. So I need to go from moles of water, moles of O2. So if I look at my stoichiometry, it takes 2 moles of water to make 1 mole of O2. So I have 2 over 1. And then I need to take 18.02 grams of water per 1 mole of water. And of course, my units cancel here. Moles of O2, moles of O2, moles of water, to give me, end up with grams of water. So let's go ahead and plug in those numbers and do the math. So 0.0518 moles times 2 divided by 1, and then times our molar mass. And to 2 significant figures, we end up with 1.9 grams of water. And so that's another example of the type of stoichiometry problem that we can do. Working with gas properties and the ideal gas law to convert it into moles. All right, so that's all for this session. Next time we're going to finish up our look at Chapter 6 on gases by looking at a couple of other ideas that we can think about with gases, and looking at what happens when gases are not, quote, ideal.